Dear friends, have a good day. Here in this video, today we are going to look at theorems on bounded sequence. Here the statement of the theorem is, if the sequence of real numbers Sn is convergent, then Sn is bounded. Here what they have given is, the given sequence Sn is a convergent sequence, then what we have to prove is that the sequence Sn is bounded. So, to prove the theorem, first off you must know what is convergent sequence and what is bounded sequence, then only you can prove this statement. Here it has been given that the sequence of real number Sn is a convergent sequence. When a sequence is said to be convergent, if the sequence Sn has a limit L, then it is said to be convergent. Since here it has been given that Sn is convergent, therefore we have taken limit n tends to infinity Sn is equal to L. Then by the definition of the limit of the sequence, what you can say is, for any given epsilon greater than 0, there exists a positive integer n0 such that mod Sn minus L less than epsilon for all n greater than or equal to n0. Since limit n tends to infinity Sn is equal to L, we mean whenever n approaches to infinity, the sequence Sn approaches to L. How do you find whether the sequence Sn approaches to L? If the distance between Sn and L are very close to 0, then we can easily say that Sn approached the limit L. So, by means of notation, here we can say mod Sn minus L less than epsilon. Mod Sn minus L, we mean the distance between Sn and L. If it is less than epsilon, what is epsilon? Epsilon is very close to 0. So, if the distance between Sn and L are very close to 0, then we can say that Sn approaches to L, which means that Sn converges to L whenever n approaches to infinity. That is, n approaches to infinity, we mean for all n greater than or equal to n0. Here n0 is some positive integer. For that particular positive integer n0, if we take higher than that of n0 for the values of n, we can say Sn approaches to L. That is why here we have taken modulus of Sn minus L less than epsilon. Now choose epsilon is equal to 1. Then what you can say is mod Sn minus L less than 1 for all n greater than or equal to n0. Here what we have done is, in place of epsilon we have replaced 1. So that is why here we got mod Sn minus L less than 1 for all n greater than or equal to n0. Now what we have to prove is the sequence Sn is bounded. When a sequence Sn is said to be bounded, if the sequence Sn is both bounded above and bounded below, then it is said to be bounded. That is, we have to prove Sn less than m for all n greater than or equal to n0. So this is the condition to check whether the given sequence Sn is bounded or not. If mod Sn less than m, then we can say that Sn is bounded. So here we have to prove mod Sn less than m for all n greater than or equal to n0. Now mod Sn can be written as mod Sn minus L plus L. Here what we have done is add and subtract capital L. So this can be written as modulus of Sn minus L plus L, which is less than or equal to mod Sn minus L plus L with the help of triangular inequality, because triangular inequality says that mod x plus y less than or equal to mod x plus mod y. Therefore, modulus of Sn minus L plus L can be written as less than or equal to mod Sn minus L plus mod L. So which is less than, mod Sn minus L is less than 1. So this can be written as less than 1 plus L for all n greater than or equal to n0. If we choose 1 plus L is equal to m, then what you can say is mod Sn is less than m for all n greater than or equal to n0, which means that the sequence Sn is bounded. Hence the sequence Sn is bounded. That's all. Thank you. If you like this video, please subscribe my channel and click the bell icon. Thank you.